Mm-hmm.
Wait, what direction? This would be south or west?
Okay. Guys, can you just set up the, just turn on the projector, please. And just pass me that HDMI as well. Thank you. Appreciate it. Just that.
This?
Yeah. Perfect.
Between these two?
Not yet, but thanks. I don't need a lesson.
I guess. But that's like not vertical, so just. And elastically, it's like they just bounce off each other. And they're like everything is preserved.
Okay.
But elastically, they just stick together.
I'm going to go over the equilibrium problem from yesterday, number 1. That's page 200 in the handout. Okay, so, gentlemen, with this setup, what's important is you draw the forces that are acting with the proper angle. You can label them whatever you want. I'll just keep it simple. F1, F2. I said to you yesterday that these are the same thing as FG1 and FG2. This here we have, this is 12 newtons. We need, I gave you these angles yesterday. We need to know what these angles here are at the tail. So this angle here is 50. This angle here is 40. So what we're trying to find is F1 and F2. I just started. Okay, no question. Not until I get at least my first statement down. Okay, so that's my first condition. It's not moving, so the force is balanced. Okay, that's what that statement says. The force is balanced. So I have here, I'll deal with the x's first. This is my F1x. I'm just going to make this more clear here. This is my F2x. Okay, so there are only two forces, so they must balance. It's not moving to the right or left. So F1x must be equal to F2x. So we'll write it this way. Write the one that's pointed to the right first, and we subtract the one that's pointed to the left. And then we break these up. We represent each of these in terms of their components, in terms of their hypotenuse and cosines. So F2x is F2 cosine. And F1x is F1 times the cosine of 40. And then we rearrange this. We could rearrange it for F1 or F2. It really doesn't matter. I'm going to rearrange for F2. Make sure that this was it done that way. Give me 1 sec here because I want to make sure. Yeah, we'll rearrange for F2. I just put F1 cos 40 on the right, and then I divide by the cos 50. Yeah, that's my equation 1. My equation 2 is going to come from the fact that it's not only not moving side to side, it's not moving up and down. Not moving up and down. So it's balanced in terms of forces. All the upwards forces must be balanced by whatever the downwards forces are. That's what this says, essentially. They must all add up to 0. So let's draw those in. That is my F2 y. That is my F1 y. So pay attention to the direction. The y components always give us a little trouble. This F2y and F1y are pointed up. So they're going to add. This 12 Newton, this is 12 newtons here. That's pointed down. So that's going to subtract. Anything in the same direction will add. Anything that's opposing it will subtract. We have F1y plus F2y. Minus 12 is 0. Okay, this is going to come in handy later. So I'll just put the 12 on the right. And now you do the same thing for the y components. Represent them in terms of their, in this case, the sine and the F1 and F2. So F1y is F1 times the sine of 40. And F2y is F2 okay. Now we're going to just see if I can represent this clearly for you. That's sloppy. Okay. So let's plug this in here. Let's take equation 1. That represents F2. So let's plug it in here with the F2. I'll put it in red just so you're a little more clear on that. Okay, so notice what I've done. I've turned this was equation 2. I've turned equation 2 into an equation that contains only F1 as an unknown. That's the whole point. And then you can factor it out. Oh. Okay. And you get F1 is just equal to 12 over all of this, over all of that. So that should work out to be that should work out to be 1.55. That is 1.55. Okay, so this works out to be 7.74 newtons. Okay, I'm not done. I only have F1 now. I need F2. That's we can get from the first equation, equation 1. We can just plug in F1. So F2, F1 is 7.74. And that works out to be 9.2 newtons. Okay, so that's your question. It's usually two variables that you're solving for. So you will need, not in all cases, get some examples I'll show you later on, where you only need to use one of these in some cases. But if they ask you to solve for 2 variables, then you're going to need 2 equations. If it's 1 variable, maybe you can get away with just 1 equation. You'll have to fiddle around with it and test it. Okay, try 3 and 4. Now, some of this is geometry, so if you're not sure how to find the angles, let me know. I can set it up for you. But try 3 and 4. Let's see if you can get the geometry right. You can try actually 3, 4, 5. We'll go over those. Those will try. I was going to do a lab with you, but I don't know what equipment tomorrow, but I don't know what equipment's available. So I'm going to take a look for equipment. You work on those, and then I'll go over them for you.
Number 4 is 4 and 5, right?
What are you finding for number 4?
Oh no, like what we're supposed to be doing right now, 4 and 5, right?
Yeah, you can do 3, 4, 5. Do 3, 4, 5. Okay, so I will check for the equipment for you.
Yeah. Also, 27. What's that? Even 42 by my father. What's the food negative tension? Which was mostly super difficult fucking. So actually, father. So this one. It's a force going forward. So you're continuously going forward. Oh, I do not. Oh, and the components of one universe and why not? And then there's only one life and two. This one doesn't have life. Or not. So, anything of the y-axis is 0. US is 1. And which part? Yeah. Don't get it. How it works. This is not a right track. The tangent should equal the number of mutants now. Which is 20. Does this thing have an average key? Sit around 20 variances. Survive free Jesus. It's probably. Oh wait, no. Yeah. What? Well, like that. Oh. Okay. Or whatever. Brush. What's actually not that bad? It's like sure, but if it is, FT1X. Because like this is stationary, what number 3 is in motion? Yeah. Same. I'll give you motivation. I'll give you all the motivation that you need. Done. I want some water. Get some. Okay. 16
You guys did the first one, or?
number 3. Number 3 is emotion.
Hmm.
Can you just say the numbers? You got it on number 3.
You want me to give the answer to 3?
Yeah.
Yeah, let's see. What is the magnitude of the tension? And there's a force exerted. Okay, so there's a force exerted by the father, and then there's an FT. The FT is 22.4.
Wait, I actually got it.
Yeah?
I actually got it.
And the F is, I guess the force exerted by the father is 10.2.
Yeah. Oh yeah.
You guys got it?
It's like you can substitute. What? Okay, so it's force of gravity, right? Yeah.
You're going to do it on the board.
Force of gravity. Yeah. So that would be this. Yeah. Oh, because this actually represents this. I wasn't expecting that.
Makes sense?
Yeah.
Got it? You got the first one? Okay. I'll go over it. Then I'll have one of you do number 4 on the board, but let's do 3 together. 3. So you've got, I would just draw the forces acting. So that's your FT. F is horizontal, so that's important to remember. That is, all there is an X component for F. And the downwards is 20 newtons. And now I'm interested in the angle at the tail. So this angle here. This angle that I need. I know this angle is 27 at the top. It's 27 here. I'll do this in a different color. So this angle here has to be, this is 90 degrees here. So this angle here must, plus 27 must add up to give me 90. So that's 63. Okay, now I can start using that angle to write down my expressions. So, 2 expressions. I would start always, if in doubt, you can write both. The general rule is if you have 2 variables to solve for, like in this case, F and FT, then you'll need the 2 equations. Start with the X. So we have an FTX. And we have an F over here on the right. So F, I always put whatever's pointed to the right, I put that first, and then whatever's pointed to the left, I subtract it. This is just another way of writing the following. F is equal to FTX. The forces balance. They're in opposite directions, but they balance each other. Cos of 63 is 0.45. So I'm going to call that equation 1. I've got an equation of F in terms of FT. We can write that this says here that all the forces add up to 0. Just another way of saying the forces balance in the y direction. Let's go back to the diagram. Let's see what we've got. We only have 2 forces acting parallel to the y. We have the 20 Newton acting down. We have the FTY component acting up. Whatever's pointed up, I usually write first, and whatever's pointed down, I subtract. Okay, FTY is just FT times the sine. So we can solve for that right away. No substitution needed for this one. No substitution needed. Just one variable in the equation so I can solve for it. Then I can plug it. Then the trick is to plug that into equation 1. $10.2. That's it. There's no hard set rules as far as when you have to substitute. You're just going to have to do lots of problems to get used to it. The general rule is set up the two equations. What are the two equations? All the forces in the x direction add up to 0. Another way of saying they balance. And then make sure you write any x components, write it out in terms of the cosine. And then similarly for y, all the forces in the y add up to 0. Another way of saying the y components balance. Any y component, some numbers you're given like the 20, it's acting down. Any y components you express in terms of the sign. Any force that's acting down, you're going to subtract. And then you can do this if you want. I put it on the right side. Sets it up so it's easy to rearrange. Yeah.
Where's FTX?
FTX is here, right? So on here, this is FTX. In the diagram, that's FTX. It's balancing this force here, F. FTX balances F. Otherwise, it'd move, right? It's not moving. It's just sitting there. So these two forces must balance each other. So FTX is the x component of FT. So I included it in this first equation.
Oh, right.
Yeah. And then I change FTX into FT times the cosine.
Like basically it's just like a snapshot of like one moment.
Yeah, it's not going to, I mean, it's at any moment, it's not moving, period, right? The force is balanced. So, yeah.
It says that the child is being pushed. So does that mean that it is
The child sitting on the playground is being pushed by her father. When the swing rope makes an angle, I think what they mean to say, and that's why sometimes they word it probably not as clearly as they want or intend. It's pushed, right? So he's pulling it back. What they mean is that basically he's pulled the child back, and then he's going to let her go, him or her go, and then he'll have to give her another push. That's what I think it means. So, but at that, yeah, I see what you're saying. Is it a snapshot, a moment in time? Most problems are not like this. Most problems, it just sits there. In this case, yeah, you're right. I got what you're saying. It's a snapshot just before he lets it go.
Do you ever have a problem with it?
It's in motion? No. These are all either a snapshot in time or stationary. Yeah, good question. Okay, so 4 and 5. Yeah. Mm-hmm. Four. You want me to zoom it? Sure. Big, is that enough? Sure. Yep. There you go. You're welcome. Yeah, 4. How did you set it up? So let's look. I'll set it up for you and let's see if this helps you. Good questions. Yeah, in any of the problems, just to backtrack again, any of the problems that we do where you have something that's hanging or it's set up to look like is in question 3, it's pulled back. There are always going to be stationary situations, at least in that moment. At least in that moment. Okay, so the diagram for number 4. This is kind of weird looking. I'll highlight a couple of things here. So this is 75 newtons. It's 80 degrees at the top there, right? If I were to draw a little line here, it's parallel to this component here. All right, this angle here is equal to this angle here. That's, I mean, you could call it, if you want, looks like this, looks like a Z. This angle here is always equal to this angle here. You call it the Z rule if you want. It's just what I said yesterday. You got a set of railroad tracks. There's a line that cuts through it. These two angles are equal. So that makes this angle here equal to 80 degrees. That helps us. We also need this angle in here. What is that? We know this angle. I'm going to erase this in a second here. That's 68. So this must be the complementary. So this has got to be 280. This has to be 22. Okay. Now, a couple of things to remember. Let me just make this a different color. Couple things to remember. Let's draw the Y components as a different color. I'm going to use purple. So they keep using all these subscripts. I'm just going to call this F2. I'm going to call this one F1. Y component here, I'll call F2Y. That's pointed up. It's important you get the directions right. Look at where it's pointed. Make sure you know which direction the component is pointed. F1Y is pointed down. F1Y, this component, pointed down. It's going to subtract when you set up the math. Okay, so let me set it up for you so you know what I'm saying. I'll come back to the X because the Y is a little more difficult. So the sum of the forces in the Y is 0. Any force that's pointed up, if there's 2 of them, they're going to add. If there's 1 of them, put that first. That comes first. I'm just writing down the absolute values now. F2Y is up. F1Y, like I said earlier, is pointed down, so that's going to subtract. That's the trick. 75 is pointed down, so it's going to subtract. I'm not going to go through all of it yet. I'll just set it up for you. The X is easy, right? This is F. Put it in green. This is F2 X. This is F1 X. So the sum of the forces in the X is 0. What does that mean? It means anything pointed to the right, put that first or add them together if there's more than one. Anything pointed to the left, subtract it. That's your setup. Those are your equations you should have. I want you to complete that. I'll complete it for you in a minute, but you try that. See what it works out to be. Okay, got it. F2y, F1y. Yeah. This is going to be a substitution. Solve for the right side, rearrange for F2. I'll work on it for you here. You can just, as I'm doing it, you just work on it yourself. So I got my first equation. So I got my second equation. I'm going to plug my first equation into the second equation for F2. Yeah. That's my F1. Then you can go back to equation 1, plug it in, find the F2. So this is F1. Now you got your F1. Whatever. Okay, and then round them off to 82 and 15. Mm-hmm.
The number 5, our diagram is cut off. Do you mind drawing it?
Oh, is it cut off?
Yeah.
Okay, give me a second. Just let people finish this and I'll draw it. Give them a minute. I'll scroll up. 5 is okay. I'll draw it in a sec here. Okay, so this is, I'll come back to this who needs it. This is the diagram for number 5. There's a mass here. It's unknown. And this is some maximum mass. You can call this FT. FT. Need me to scroll down? Back?
No. Is that empty?
FT. Mm-hmm. I'm going to go over 5 in a second here. For those who are done, you're going to have to do this anyways. Try 7 and 8. I don't know if I'll give you time in class here. We'll see. On the 7 and 8. I'll go over 5 in a second.
Wait, this is not six, right?
I'll do 5 now. Call this F. Hmm. Hmm?
I just wanted to scroll.
You want me to go over that? Capiche? Yeah, I'll put 0.5. You guys will get confused. About 2.3. You like my color coordination? X components are red. Y components are purple. You don't like my color coordination? Red and purple. I try. I aim to please. Sure. Like that? You mean up, down? Up. I make it bigger? That's my chart. Sorry, didn't mean to show you that. Examples of translational. Translational. That's cool. This looks dumb. But she looks. I always get punished if I. Don't go for the dumb one. This looks kind of. Okay, what the hell? I just need that. You got that here. You got that audio jack. Don't lie. This is 2 minutes. This is 7 minutes. Which one? This one has lots. Yeah, that's okay. Translational equilibrium we'll get to next. We'll try a couple of these. Don't laugh. I feel like I'm teaching elementary today. Draw the forces acting on that box. Draw the forces acting on the box. It's in translational equilibrium. You just lost a gummy bear. Stop it. Yeah, don't snicker. No stars for you. Tick, 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 tick. You gotta admit, the music kind of sticks with you. You ready for the big revelation? Here we go. Oh, don't ask a question about this one. This is like kids' video. You know that already, right? It's not moving, so the forces all add up to zero in each direction. Right, we were told earlier on that he's applying a 200 Newton force. So the only opposing force, like you said, is a friction force. So that must be 200 in the opposite direction. You ready? I know you just love the music, so here we go. We usually use capital N. That lowercase n stands for normal force. Yeah.
question about the swing problem.
Yeah.
So my father is pushing the
Yeah, that's the thing I think what they mean is at that point he's just pulled. You know how when you're gonna basically you're setting the kid up so that he's able to. You pull him back first, and then you let him or her go, and then she starts to move, and then you have to give her a push, right? That's what they're for. But don't worry about the after effect. All we're interested in is the first part where you pulled her back and you're about to let her go. It's always a stationary point in time where it's not moving. I know. It's such a cool video.
animator.
I shouldn't. Is there anything that actually is
0 comments.
no comments?
No comments.
Oh my.
Less than how views.
Okay, let's look at what these guys say. Might not be funny though. This is where we're doing next, torque. Okay, one more video here. Let's see this.
Grammarly helps you work more efficiently, which makes a
Good morning. An object is in equilibrium if the
Wow, man. I thought my shirts were bad. Okay. Tie-dye. It's okay. It's cool.
net force acting on that object is equal to 0. Flippin' physics. Billy, if the net force acting on an object is equal to 0, what is happening to the object? An object in equilibrium has a 0 net force acting on it, so it isn't moving, right? An object that is not moving.
How does he do that? Like he's got 3 copies of himself. Post. You edit a lot, or yeah, you do a bit. You do a bit. You do a bit. Yeah. Okay. You do a bit. Okay. Impressive.
Is in equilibrium. However, an object in equilibrium is not necessarily at rest. In other words, if an object isn't moving, it is in equilibrium. However, an object that is moving can also be in equilibrium. Bobby, please use Newton's second law.
Yeah, to keep it simple, we usually just deal with objects that are at rest. It could be moving at constant speed and the forces would still balance. We don't deal with those problems, but that's what he's saying. It would be the same diagram for an object that's moving at constant speed, either sideways or up and down. Yeah.
So you can say that the total force equals 0, but the acceleration is
Yeah, the total net force is 0. Yeah. So yeah, if you add up all the forces, it's the same thing as saying the net force. Yeah.
In this concept. Well, Newton's second law tells us that the net force acting on an object equals the mass of that object times its acceleration.
Where both acceleration and force are vectors.
Right. And if the net force equals 0, then the acceleration of the object is 0. And acceleration equals change in velocity over change in time, so the change in velocity of the object is 0. Yeah, so if an object is in equilibrium and moving, it will maintain a constant velocity. Correct. When an object is in equilibrium, the net force acting on that object is equal to 0. And according to Newton's second law, the net force is always equal to mass times acceleration. Therefore, the acceleration of the object is equal to 0. And acceleration equals change in velocity over change in time. Therefore, the change in velocity of the object is equal to 0. Therefore, the velocity of the object is not changing. Which means an object in equilibrium is either at rest or moving with a constant velocity.
Yeah, so again, we deal with the cases where it's at rest. Keep it simple.
Isn't an object at rest maintaining a constant velocity of 0?
Yes.
Yeah. Sometimes people refer to equilibrium or all the forces adding up to 0 as the forces balancing out. In other words, all the rightward forces balance out with the leftward forces, and the upward forces balance out with the downward forces. So equilibrium, all the forces balancing out. Let's talk about some examples. This book on an incline is an object at rest. Bobby, what are the forces currently acting on the book?
The force of gravity is straight down. The normal force from the table is pushing up and perpendicular to the table. And a force of friction is parallel to and up the incline.
Correct. And when we add all those forces together, they add up to 0, which is
when it's not moving. When friction is strong enough to offset the parallel component of FG. If it's just sitting there.
why the book is still at rest, because the book is in equilibrium. Now, let's look at a vehicle moving at a constant velocity. The forces acting on the car are the force normal up, the force of gravity down, the force applied forward, and the force of friction backward. It is an object in equilibrium, so all those forces add up to 0. The net force in the y direction equals 0, the net force in the x direction equals 0, and therefore the net force in all directions equals 0. Therefore, the car continues to move at a constant velocity. This type of equilibrium is called translational equilibrium, which means non-rotational equilibrium. Translational equilibrium, where the net force acting on an object is equal to 0, therefore the object is
Translating.
either at rest or moving at a constant velocity.
Translational equilibrium means it's not translating. We use that to describe motion side to side or up and down. It's just sitting there, or it could be moving at constant speed, but we're not dealing with that. For our problems, it's just sitting there, not moving left or right, not moving up or down.
Velocity. Thank you very much for learning with me today. I enjoyed learning with you.
Yeah, okay, that was good. We got some time left. Do a little intro here. I'll come back to this. Yeah.
Let's do a chemistry video.
No.
Are
Are they? Which one? I mean, yeah, he's good. You like him? Okay, give me a sec. We'll play a bit of them because this is an hour long.
Oh, hello. I want to see your appointment.
What?
I'm having an appointment, so I'm here to help
I'm
you.
not. I don't care about coupons.
In this video, we're going to go over a few static equilibrium problems. Now, there are two things that you need to know.
Okay, he's going to deal with torque. We haven't talked about that. I'll show you a video on torque. So at least you got an intro. No more translational equilibrium. Rotational. Okay, so you like this guy. We'll do a little intro for him.
So let's say if you have a door, and if you apply a force at these three locations.
Yeah, you do want to take some notes on this. This is a good explanation. This is a
Let's
good.
say at point
We'll
A,
finish it later when we get back from break, but we'll start with it.
and C.
So this is the door. You're looking at it, an overhead view of the door. This is the pivot where it swings from. That's stationary. This is the door here. It can swing either clockwise or counterclockwise. Clockwise is the direction that the clock hands move. It's this way. That's clockwise. Right? The hands of a clock move in this direction. That's clockwise. Anything in the opposite direction is counterclockwise.
Is it easier to push the door at A, B, or C? What would you say?
All right, that's the question. Don't tell me, but to write it down. Is it easier to push the door from point A, B, or C? Let's say it's a heavy door. Don't. Shh. All right, this is the pivot. This would be where the door handle is. This is looking downwards. It's kind of a strange view, but either looking up or looking down directly under the door. So the lever, the door handle would be somewhere around A here. B would be the middle of the door. C would be right next to where it swings. This is a door here. You're looking down onto the door. This here is the pivot or the swing point where it's attached to the wall. So it can rotate either this way and swing this way, or let's say it can swing that way. Let's say it's a strange door. It can swing. You know how they have those doors in the cafeteria that can swing either way when you enter a kitchen? Let's say it can swing either way. Where is the easiest point to push from? A, B, or C? A, yeah, this is where the handle is. That's why the handle usually is there. Most people press here because it's easiest to press it. If you press in the middle, it's harder. If you press,
You'll find that it's a lot easier
if you press near the swing point, it's really hard.
to push the door at position A, but it's very, very difficult to push it at position C. And even though the forces are the same, there is a quantity that's different, and that quantity is known as the torque. Torque is the force times the moment arm or lever arm. In the case of position A,
Yeah. This R, yeah, okay, he'll go over that in a second.
the moment arm is greater than that of position B. And so it's easier to move the door at position A than at position B because you can produce a greater torque at point A. At point B, to generate the same torque requires about twice the force as in position A. So it's a lot harder to move the door at the middle or even at the edge of the door on the left side.
Okay, yeah.
What is R in this case? What did you say? What is
All right, we're going to go into detail. That's the lever arm. It's called the lever arm. In this case, it's just measured from where the pivot is to where the force is touching. That's all it is, if it's a perpendicular force, but we'll get more into that later. This is just an introduction. This is a new quantity. It's a definition. Again, you just have to know it. It's called torque. And torque is like a net force, except torque results in an object like this door rotating about some pivot point. You've heard about the torque in the wheels of a car? So the torque has to do with rotational acceleration. How quickly you could, if you were able to push on this continually, how quickly would it accelerate in a circular direction? Yeah.
What's the unit?
Yeah, we're going to get into that later. But this is obviously, this is newtons, and this is meters. So the unit for torque is Newton meters. Okay, so our foot pounds is the imperial, right? You know how you have a torque wrench? Yeah. I think you can get it in Newton meters, which we usually don't work with. We tend to work with foot pounds or, yeah. Okay, to take your break, you got till a couple of minutes after 10.